So my project was assessing the climate-water balance model's ability to predict soil moisture variability and species distribution of a forested watershed in the northern Cumberland Plateau. So I had a lot of fun working through this project, and I'm excited to show what I did over the course of these past 2 years. So I'll start with a background of this research and then walk through my two objectives, which were pertaining to soil moisture variability and then tree species distributions. And then I'll close with overall conclusions. So I want to start with thinking about the role of topography and how that has played in modifying patterns of hydrology, soils, microclimate, and vegetation distributions. And what I mean by this is patterns of drainage we might see, or how soils form, or how microclimates vary within the same landscape. And the role topography plays in modifying some of these patterns and processes in ecology has been studied for decades and has been well known, which is why I wanted to include some of the photos on the right, which are from Braun's 1942 study. So even she was describing some of these patterns throughout Appalachia. And so many of these dissected landscapes, which Appalachia would be, have shown how these patterns of topography can modify different parts of ecology. And so when I say topography, I'm really thinking about different terrain elements, which is typically how it's been studied, which would include slope aspect. So this would mean, is it a north-facing slope or a south-facing slope? And this really modifies how solar radiation is distributed. Slope curvature, so this would be, is the site in a concave or a convex area? Slope steepness. And then topographic position, which describes where along that slope is the site falling. Is it more in the valley, or is it more on a ridge top position? And so now I'm going to walk through 3 studies that kind of look at this to give you an idea on how this might be studied. The first is from Hutchins et al., which looked at the influence of soils and microclimate on vegetation of forested slopes. And so this was done in Robinson Forest in eastern Kentucky. And so they look at many different patterns that I mentioned in the first slide. The first would be looking at microclimate. So this is a figure looking at different air temperatures on opposing slopes. So the hot slope in this figure is the south-facing slope compared to the cool slope, which would be the north-facing slope. So you're seeing that difference in radiation and how that might influence microclimate. This next table is where they were looking at soil properties. And so by no means am I wanting you to look at all the details, but I just want to point out how they were dividing it and looking at it in relation to topography. So here are all the soil factors they looked at. And they divided this between slopes. So we have the southwest slope and these top 3 categories. And then the bottom categories are the northeast facing slope. And then within each of these slope aspects, they've divided it by topographic position. So here we have the upper third, middle third, and lower third. And so they're seeing how different soil properties are changing in relation to these terrain elements, how texture or pH might change. And then the last component of this study I want to point out is vegetation distributions. So they're looking at tree species in relation to these same elements. So we have southwest and northeast, so different slope aspects. And then we have 3 topographic positions listed below. So they've shown where each of these tree species are occurring and what sites they occur most on. So beginning to think about how an ecology study might look at all these elements and how topography is modifying some of these patterns. Now I want to walk through Braun's work and just a snapshot of one of the things she looked at. On the left, I thought that this was a really nice figure for kind of breaking down how this might be studied. So here on the left, we have a north-facing slope and then a south-facing slope. and then what she considers a ravine area. And we have different sites along each of these slopes, which act as different topographic positions. And then on the right, she's noted where these tree species are found, what sites those are found on. For instance, Fagus granifolia, which is American beech, is occurring more at these lower topographic positions, those 1s and 2s, compared to a species like Quercus montana, which is chestnut oak. It's appearing at these higher topographic positions, the south-facing area, which you can see over here on the left. So Whitaker, another well-known ecologist, also looked at the same sort of pattern. On the y-axis in this figure is elevation, and then on the x-axis, there's different topographic positions as well as slope aspects. So on the left, we have coves and canyons, sheltered slopes, all the way up to ridges and peaks. And so he's noted where these different forest communities are falling within these two gradients, which is very similar to seeing how these topography is modifying vegetation distributions. From this figure, I also want to note at the bottom, he has a moisture gradient, so it goes from mesic to xeric. And so this is telling us both where these species are found and where these communities are found, but also where these topographic positions and slope aspects are falling along this moisture gradient. So taking this well-known knowledge that's been documented over the past few decades and throughout Appalachia, I want to think about how they were using really descriptive variables and what they see in the field to describe some of these patterns that they're seeing. And they're also using moisture gradients that are from xeric to mesic and not totally quantifying this. So we're moving from that descriptive approach to a GIS approach. And so now with GIS technology, we can derive many of these terrain elements using GIS. And what this might look like is shown on the right. So here are 6 different terrain elements that I've derived using GIS. So first we have slope steepness, southwestness, which is a measurement sort of like aspect, and it's actually derived from aspect. And so it'll tell us from -1 to 1 how southwest is that site, with -1 being northeast facing and 1 being southwest facing. We then have relative slope position, which really acts as a measurement of topographic position. So it's from the valley, which would be a value of 0, to the ridge, which would be a value of 1. We then have solar radiation, which is calculated using ArcGIS. And you can really see how the influence of slope aspect is influencing how much solar radiation might be experienced. So this southwest facing aspect is receiving much more solar radiation. We then have plane curvature, which indicates is the site convex or concave. And lastly, I have put the topographic wetness index, which is a relative moisture index. So areas of dark blue indicate you're likely to experience more moisture on that site compared to a lighter blue. And so I talked about how Whitaker was using this xeric to mesic moisture index. I would then want to segue to GIS moisture indices. So 2 of the very popular ones that have been used are the topographic wetness index and then the integrated moisture index. And what this might look like is shown by the topographic wetness index here on the lower right-hand corner that I just mentioned. And so it's calculated using the upslope contributing area and then slope steepness. And so it's really trying to capture those patterns of drainage you might see in a landscape. And so although some of these moisture indices have been shown to correlate with patterns of soil moisture you might see in the field, there are some disadvantages to using them. And particularly when we're thinking about climate change, static versus dynamic variables becomes a point that I want to talk about. So these GIS variables are static, so they're not going to change throughout the year. The patterns of soil moisture we see portrayed by the topographic wetness index isn't going to change throughout the year, and it's not going to reflect differences in precipitation or differences in temperature, or even year to year, that pattern won't change. I I also want to point out that we might want to look at variables that reflect plant relevant resources. So topographic wetness index is a relative moisture index. It's not telling us the quantifiable amount of moisture on that site. Rather, it's showing us just a relative moisture index. So it can't exactly be compared between two different landscapes, or even within a landscape, it's not telling us a specific amount of moisture. So with that in mind, I will now start talking about the climate-water balance. And this is a concept that looks at the simultaneous availability of usable water and energy. Another way to think about this is the evapotranspiration demand supported by the water available? So we know that throughout the year, evapotranspiration demands are going to change, and precipitation trends are going to change throughout the year, and they'll probably vary year to year. So being able to look at a variable that captures both how much energy is at that site as well as how much water is available at that site is both a dynamic variable and also one that is more plant relevant. So a part of this climate-water balance concept, there are many variables, including potential evapotranspiration. So this is the rate of evapotranspiration under unlimited water. So this is a hypothetical scenario where that system that you're looking at has unlimited water to support that evaporative demand. Then there's actual evapotranspiration, which this is the evapotranspiration rate under limited water, or the water that's experienced in real time. And when there's not enough water to support that PET, there is a water deficit. And when there is more water than is needed for that PET demand, there's a water surplus. So this has the ability to capture more of that dynamic, how it's going to change throughout the year or change year to year of water balance, and also looking at a variable that's more plant relevant. So Stevenson in 1990 showed how two of these climate-water balance variables could be used to differentiate between plant biomes. So it's really looking at that continental scale. And he showed that a southern mixed coniferous forest has a high rate of AET, which is on the y-axis, and low rate of annual deficit, which is on the x-axis, compared to a warm desert, which would have a pretty high annual deficit, but a low annual AET rate. Lutz et al. In 2010 showed this similar idea, same variables, so annual AET on the y-axis and then annual deficit on the x-axis, except at a landscape scale. And so they were looking in Yosemite National Park at individual tree species and how they were differentiated between these two climate-water balance variables. So we introduced that climate-water balance idea. Now I want to talk about how it's been applied as a GIS variable or a GIS toolset. So Dyer in 2009 created this GIS toolset that you can import into ArcGIS. And with some user data I will talk about next, you can create and calculate these climate-water balance metrics for your study area. And so this toolset really points to this question of how does topography modify solar radiation load and subsequently evapotranspiration rates. So it's tying together both how topography is modifying some of these patterns, but also what are the evapotranspiration rates within that watershed or within that study area. And so the input data can either be user provided or downloaded from publicly available databases. And they include a digital elevation model, which really represents the surface terrain of the area. Solar radiation data, which can be found from the National Solar Radiation Database. Climate data, which can be found from PRISM Climate Group. And lastly, soil available water capacity, which can be downloaded from the NRCS Surgo database. So it's really capturing solar radiation, the topography of the area, as well as climate and soil data. And so once that data is inputted into this tool set, You can select what time period you want to calculate climate water balance for, and the output is in the form of monthly and annual rasters, which represent PET, storage, AET, deficit, and surplus. And so on the right, you can see what maps, or what these maps might look like. So to orient you, in this watershed, the stream is in the middle, and then we have the north-facing slope and the southwest-facing slope. So this is the PET map. And you can see how the southwest-facing slope is experiencing higher rates of PET. Next up is the storage map, which this is informed both by precipitation and the soils map from the SERGO database. We can tell that the north-facing slope has a higher rate of storage compared to the southwest-facing slope. And this is really a function of that SERGO database soil data. And so that's informed both by texture and soil depth. And so we can tell by this map that the northwest or the northeast facing slope is able to retain more of that moisture because of the soil properties in that area. So both the PET and storage go into determining AET. And so you might notice that the north-facing slope has higher rates of AET, and that's because we had more moisture from the storage map to support those evapotranspiration needs. And the last map I show is the deficit map. So on the northeast-facing slope, there's low deficit compared to the southwest-facing slope, which there's pretty high deficit. So that gives you an idea of what that might look like and how that's used. So Dyer, the same person who created this GIS toolset, looked at both how it can be used to represent soil moisture as well as tree species distributions. And so in this study, he was looking at soil moisture at two different landscapes, one in Ohio and one in North Carolina. And so he had soil probes throughout these landscapes and showed how soil moisture in the field could be represented by soil moisture from the model. And he was reporting correlation coefficients of 0.92 to 0.97, so pretty high. And then when looking at the tree species distributions, I'm mainly interested at this on the left-hand side of this figure. So he has a summer deficit from that toolset output. So June, July, and August deficit. And then he's shown where these tree species are falling along this site. So in the left, we have more mesic species such as beech and tulip poplar at the lower end of this summer deficit. And then we have species like chestnut oak and black oak at the upper part of this summer deficit. So he did show that it was able to pretty well differentiate between some of these species. But next, I want to point out a knowledge gap that we looked at. So this GIS toolset doesn't take into account topographic position and how it calculates available water. And I think a good way to show the importance of this is to show a table from Stevenson 1998. So there's a lot of information, but I'll walk through it. So on the left-hand side, we have different studies that have created topographic moisture indexes. And on the right, we have what factors they included when calculating this. And Stevenson's divided it in two areas. So we have on the left, factors affecting evaporative demand. So that's one part of the climate water balance. And then on the right, there's factors affecting water availability. So the numbers indicate whether that factor was included in that study and what the ranking was. But mainly, I want to point out that slope position was included in all but one of these studies, which points to the fact that it is an important factor in describing some moisture that we see in the field. But I will say that this GIS toolset does include aspect, slope exposure, as well as soil water holding capacity. So it is including some of these really important factors that we see listed. So with that, we wondered, without including slope position, how do GIS climate water balance variables represent soil moisture and tree species distribution in our study area? And also, do GIS climate water balance variables and GIS terrain variables differ in their fitting power and prediction power or patterns. So when I say GIS terrain variables, I'm thinking about slope steepness, relative slope position, topographic wetness index, some of those variables that I mentioned earlier. And then the GIS climate water balance variables would be the PET, AET, those variables created from that GIS toolset. So with that, I want to introduce my two overarching objectives. To assess the ability of the climate water balance toolset to first represent soil moisture variability at fine spatial resolutions. And secondly, to explain tree species distributions in a dissected landscape. So the study area for this research was Little Mesquite Watershed, which is located in Robinson Forest in eastern Kentucky. And so this area is part of the mixed mesophytic forest region as defined by Braun, with parent material of sandstone, siltstone, and shale. And it's characterized by steep slopes, which can affect both the soil formation, drainage patterns, and possibly tree species distributions. So I wanted to give you a few more photos to give you an idea of place. So we have mesic and xeric sites, and here's the valley and ridge. So for both parts of this study, the soil moisture and vegetation distributions, we had 100 plots. They were distributed across three factors. The first is slope aspects. So here's the north-facing slope and the south-facing slope. The stream runs in the middle of the watershed, and then here is the north-facing ridge and the south-facing ridge. The next factor would be topographic position. So we had 5: ridge, upper slope, middle slope, lower slope, and valley. And then we had 2 slope curvatures. So this transect on the left would be considered a convex slope curvature. And then we had ones that were more concave, such as this one. So we established these plots in late May of last year. And so we recorded GPS coordinates using that really cool hat. And all of our coordinates except for one, so 99% of them, had an accuracy of less than 1 meter, which was important since we're really looking at these GIS variables, so we care about the accuracy of the GPS unit. So first, looking at the first objective, which is the soil moisture one, we had 2 specific objectives. First, to assess and compare the explanatory power of commonly used GIS terrain and climate water balance variables in explaining soil moisture. And secondly, to evaluate model performance of terrain, climate water balance, and the combination of these categories and representing field measured soil moisture. So the first part is really looking at what is the variable ranking of GIS terrain and climate water balance categories. And then the second part is really looking at model performance. So for our field measured soil moisture, we collected soil moisture measurements from 100 plots that I showed earlier. And so we had 2 methods of doing this. The first is using TDR, and the instrument for doing that is shown on the right. So at the bottom of that instrument, there are 2 probes that go into the ground to about 8 centimeters, and we'll take 5 measurements per plot and take an average of that. And so those are reflecting volumetric water content. In addition to these TDR measurements, we also took gravimetric water content measurements. So that required taking soil samples from each of the 100 plots. I would then take a subsample and weigh that soil wet and then dry it for 24 hours, weigh it dry, and then I could then calculate the gravimetric water content, which is a by weight measurement. So in addition to these measurements from all 100 plots, I do want to mention that we did have time series data that we collected from June through October. So we installed these microstations that sit there and record soil moisture every 10 minutes. For that whole time period. However, these were only at 20 plots, so we weren't able to incorporate it in the main part of our analysis, but I did want to mention that we do have some pretty interesting data from this time series data. So we have the soil moisture from the field. Then to compare it to GIS variables, we divided our variables into 3 categories. The first is that terrain category. The second is climate water balance. And the third is a combination of all variables in the previous 2 categories. So here are the GIS terrain variables that we use. And you've seen this, this figure earlier in this presentation. So first we have slope steepness, southwestness, relative slope position, solar radiation, plane curvature, and topographic wetness index. And so these are all rasters representing continuous data. And so once we have that calculated for this study area, we then extracted the values of those 100 plots for each of these predictor variables. Next, we have the GIS climate water balance variables. So we collected the soil moisture that we were using in July of 2019. So that's the month that we were using climate water balance variables from. And for this month, it had pretty high precipitation, so there wasn't a deficit, which is why it's not included as one of the predictor variables. But we did have PET, soil moisture storage, and then surplus. And so once again, we extract the value of those 100 plots for each of those predictor variable rasters. So for the statistical analysis, for the first part where we wanted to assess and compare the explanatory power of variables, we used a model averaging approach using the dredge function in R. And then for evaluating model performance and representing the field measured soil moisture, we first identified the top models using Stepwise AIC. And then to formally compare model performance, we used the non-nested likelihood ratio test to compare models. And that's using the Baum test in function in R. So now I'll walk through some of our results. So first looking at that variable ranking from model averaging, I'll orient you to the table first to not overwhelm you. So on the far left, we have the soil moisture metrics, so gravimetric water content on top and then TDR. We then have each of those models, so terrain, climate water balance, and combination. And then we have the ranking of the variables in each of those categories. And so this ranking is from the sum of weights. So in dredge, we had a subset of models from a delta AIC of 4. And the sum of weights is really influenced, one, by how many models that variable is included in, and also the weight of those models. So a higher ranking variable is performing better. So for gravimetric water content in the terrain category, the top variables were RSP, so relative slope position, and southwestness. For climate water balance, the top variable was storage. And then for the combination category, it was a combination of those 3 top variables, so relative slope position, southwestness, and storage. We see similar results for TDR. So for the terrain category, RSP is a top variable, so that's relative slope position. Climate water balance had storage as the top variable. And then in the combination category differed slightly from gravimetric water content, but the top ranking variables were storage, RSP, and slope steepness. So from this, we can kind of get an idea of what variables are performing better. To really evaluate model performance, I'll now move to Stepwise AIC, which is where we identify the top models. And there's a lot going on in this table, but from it, I really want to point out the R-squared values so we can start to get an idea of how these models are ranking against one another. So for both gravimetric water content and TDR, the combination model performed best, so it has the higher R-squared value compared to the other models. Second, we have terrain for both soil moisture metrics, and then the combination model is coming in last. So we kind of get this idea of what's going on, but to more formally test the differences between these models, we use the non-nested likelihood ratio test. So we're taking those top stepwise models and using the non-nested likelihood ratio test. So one result that we see from both soil moisture metrics is that the combination model is fitting better than the climate water balance model, which is telling us that including these terrain variables with climate water balance variables is improving model performance rather than just using climate water balance variables alone. Interestingly, the combination and terrain models weren't significantly different, even though the combination model was having a higher R² value. So from this first objective, I wanted to note that storage is the top climate water balance variable. And so I want to refresh what that looks like. So it's found in this upper right-hand corner. And so you'll see that there's only 3 values for this study area during this time. And that's coming from that Surgo soil database, and it's a very coarse resolution. And in months with high precipitation, this tool set is pretty coarse in how it represents soil moisture storage. So even though the GIS tool set isn't using topographic position and how it calculates available water, I think that storage is being chosen in part because it might be coarsely representing some of this pattern, but having a ridge top position value for the whole watershed. So it might be mimicking some of those patterns we might see with topographic position. RSP was a top variable in both terrain and combination categories, which it's in the upper right-hand corner. So it's showing us topographic position and where that site falls within a slope. Southwestness was a top variable for gravimetric water content, and then slope steepness was a top variable for TDR. So there was slight variation there, but overall, both the soil moisture metrics showed the same trend. When evaluating model performance, we found that the combination models perform better than climate water balance models, which tells us that including terrain variables does improve model performance. And lastly, we note that the terrain and combination models weren't significantly different, even though the R² was different. The non-nested likelihood ratio test showed us that that wasn't a significant difference. So we just addressed the first part, the first objective, looking at soil moisture variability. Now I'll move on to the second objective of looking at tree species distributions. So like the first objective, we had different parts to this objective. The first 2 are the same. So we first wanted to assess and compare the explanatory power of commonly used GIS terrain and climate water balance variables in explaining tree species distributions. Secondly, we wanted to evaluate the model performance of terrain, climate water balance, and the combination of terrain and climate water balance models. Third, this was different than the first objective, but we wanted to compare the spatial prediction patterns of species by each of these models. So models in terrain, climate water balance, and then the combination category. So for the data collection, we had a fixed area plot design that was 1/50th hectare, which is about a radius of 8 meters. And so we were measuring trees within those 100 plots that had a diameter at breast height of greater than or equal to 12.7 centimeters, which is about 5 inches. So as we had before, we have 3 GIS variable categories. The first is terrain, the second is climate water balance, and the third is the combination of all variables in the previous 2. So the GIS terrain variables are the same as our first objective. We have slope steepness, southwestness, relative slope position, solar radiation, planned curvature, and topographic wetness index. The only difference is that when we extract the values of those 100 plots, for this objective, we used a 9x9 cell focal mean, which will reflect that this the plot design for this objective was larger at 1/50th hectare, so we wanted to have a focal mean to reflect that. Here are the GIS climate water balance variables we used for this objective: EET, storage, AET, and deficit. So I showed these maps earlier, so you should have a pretty good idea of what those patterns are. And for this part of the objective, we used a June, July, and August cumulative value from the year 2007. And we chose this year based on it's high deficit. So I calculated climate water balance from 2000 to 2019, and I was looking at the growing season deficit for each of those years. And so 2007 had a pretty high, or the highest deficit of that time period. And so once again, we extract the values of those 100 plots, and we were using a focal mean to reflect that larger plot area. So now I'll walk through the statistical analysis. We used generalized linear modeling using logistic regression, and we were using presence data of the top 6 most prevalent species, which for our study area were Acer rubrum, or red maple, Fagus grandifolia, or American beech, Liriodendron tulipifera, tulip poplar, Quercus alba, which is white oak, Quercus montana, chestnut oak, and then Quercus volutna, black oak. So the statistical analysis reflects what we did in the first objective. So first, looking at assessing and comparing the explanatory power of the variables, we were using a model averaging approach to identify those top variables. To evaluate model performance, we were using Stepwise AIC to first identify those top models, and then using non-nested likelihood ratio tests to compare the models to one another. And then for comparing the spatial prediction patterns of each species, each of the models in those categories, we used the top models from Stepwise AIC and then created prediction maps, and this was done using the prediction function in R. So I'll walk through some of the results. Looking at that variable ranking from the model averaging, the table is the same format as the first objective. So we have species in the left, the models next, the ranking of the variables, which are based on the sum of weights. And so now I'll just show the rest of the species that we looked at. So one of the things I wanted to point out from this table, I know it has a lot going on, but RSP, which is relative slope position, appears as the top first or second variable in both the train and the combination categories for almost all species. The exception would be Quercus volutna, which it doesn't appear in this combination category, but otherwise we see that relative slope position is a high ranking variable. From this table, we can also see that measurements of solar radiation also rank fairly high. So this would be southwestness, which was SW, solar radiation, or any of those measurements that are coming from the climate water balance tool set, because those really reflect those differences between the slope aspect. But other than that, the ranking order does vary through different species, because of course, different species are going to be drawn to different sites and be affected by different variables. But we do see that those reoccurring themes of relative slope position and measurements of solar radiation. So now I'll move on to the model selection part. So we once again have species on the left, the different models, and then the top model from that category. And so here are the rest of the species. From this table, I want to point out the AUC score, which is the area under the curve, and then the pseudo R-squared scores for each of those models. And so the general trend that you can note is that for both AUC and pseudo R-squared, the largest value is for the combination category for each of those species. The second largest would be for the terrain category, and then the third is the climate water balance category. So we start to see this separation and how these models are performing. To more formally look at this, we used the non-nested likelihood ratio test. So we're taking those top models and comparing them to one another. From this table, I want to point out these 4 species. So these are the ones that had significant differences between the models. Acer rubrum at the top, and then Quercus volutna at the bottom didn't show statistical differences between the models. But these 4 middle species do show some differences. Mainly, all 4 species show that the combination model is fitting significantly better than the climate water balance model, which is the same pattern that we see in the first objective. For 3 of the species, we see that the terrain model is fitting significantly better than the climate water balance model, which is interesting, and that's not a result we found in the first objective. So now I'll point out some of the species prediction maps. So once again, that's taking the top models and seeing how they can predict where those species are found. And so to orient you to how this is working, we have American beech, and then we have 3 maps. So the first is terrain, the second is climate water balance, and then the third is that combination category, which is both terrain and climate water balance. A darker blue in these maps will indicate a higher likelihood of finding that species on that site, whereas a lower value of 0, which would be represented by a brown or a darker brown, indicates that you're not as likely to find that species on that site. So just by looking at American beech, we can start to pick up on some of the patterns that we're going to see in the other species. One is that we do see the influences of topographic position portrayed by terrain in the combination categories. So you can see that American beech is being found at those lower topographic positions. You see the same trend in the combination map. You don't, however, see this in the climate water balance map. It's more of a blanketed value for this northeast facing slope. The second trend that we start to see is that the terrain and combination categories are able to have a higher prediction value, so a darker blue, compared to the climate water balance variables. So the combination category in this instance has the darkest blue. It's showing it at lower topographic positions in this cove setting. The terrain category is more restricted to the northeast facing slope, but still lower topographic positions. But the climate water balance doesn't have a dark blue. It's not showing differences within a slope, and it's also not picking up on this cove setting. So hopefully you'll start to notice some of those 2 patterns I mentioned. So once again, terrain and combination maps are having higher prediction values and also showing more nuanced patterns and able to differentiate between slope position, whereas the climate water balance category is more of a blanketed value across that northeast facing slope. We then have white oak. So same type of patterns we're seeing between the models. We're seeing that it's at middle to lower topographic positions on the southwest facing slope. We see the same patterns portrayed by the combination map. And then lastly, I'll point out the chestnut oak. So we really know this species is confined to those upper slope or ridgetop positions, which is actually portrayed by all 3 of these maps. But we do see that the terrain and combination maps have higher prediction values. And it's also more distinct, where you're expecting to find the species compared to the climate water balance, which does have this middle value of prediction sweeping the southwest facing slope. And so this is a pattern that's reflecting the input data we use in the GIS toolset. So that's coming from the Sergo database soil. And so like I mentioned in the soil moisture objective, I think that that's really reflecting or mimicking a topographic position, because we know that GIS toolset doesn't directly incorporate topographic position into it. But I think that the soil data is almost reflecting that coarse pattern. And so I just want to re-show you these maps to kind of revisit what that looks like. So we have the climate water balance variables on the left, and then the terrain variables on the right. And if you look at the climate water balance maps, you'll start to see what pattern I'm pointing out. So we also see this line in the AET map, and then in the storage map, you'll see it's kind of dividing the study area. So that's that coarse pattern I'm talking about. But if you look at the GIS terrain variables, they can be much more nuanced. So I think they're able to capture some of those nuanced patterns of species distribution, and also particularly looking at relative slope position, able to reflect those topographic position nuances that a lot of species seem to be reflecting. So looking at the conclusions from from objective 2, first assessing and comparing the explanatory power of the variables. This really does vary based on species, but we do see reoccurring top variables, which would include RSP, solar radiation, southwestness, and storage. When looking at the model performance, we saw that the terrain model performed better than the climate water balance model for 3 species, and that the combination model performed better than the climate water balance model for 4 species. And then when looking at the spatial patterns of species predicted by each of these models, we saw that the terrain and combination maps have higher prediction values, and that the spatial patterns of climate water balance varied when compared to those portrayed by terrain and combination. So the climate water balance appears to be less nuanced, and the patterns from the soil data are pretty evident. And we note that the soil or slope position is important in describing some species. So all the species that I showed do show to some degree an affinity to a certain slope position. So I'm thinking about Quercus montana or even Fagus grandifolia. So they're found within certain parts of that slope. So overall conclusions from this whole study, the first would be that the climate water balance variables alone do not perform better than terrain variables. And so we saw that with the pseudo R-squared, the R-squared values, and the AUC scores. But when we tested this using the non-nested likelihood ratio test, the difference in performance wasn't significant for soil moisture or for 3 of the species that we looked at. We also saw that the combination model performed better than the climate water balance model alone, which really tells us that including those terrain variables can be advantageous. And we note that the terrain and combination models were not significantly different, which is a pretty interesting finding. We also note that RSP is a reoccurring top variable in both parts of this study. So including slope position either within the climate water balance toolkit or in those metrics or in tandem with them might improve model performance. And so we think that we're seeing this pattern because slope position describes many ecological processes influencing both moisture and species distribution, which would include the movement of materials and nutrients downslope, which could influence hydrologic patterns, nutrient concentrations, organic matter, or even soil thickness. This can also describe exposure to solar radiation and shading effects. So temperature could be different within this slope because of those differences in solar radiation or how exposed that site is. It could also lead to differences in evaporative demand. So slope position is capturing some of these ecological patterns and processes. So that's why we think that RSP is selected as a top variable in both parts. So although climate water balance variables don't perform better than terrain variables in this watershed, I do want to say they do have advantages, and specifically looking at that temporally dynamic variables or representing moisture in a plant relevant way. I think this is an important difference to point out because I think climate change is obviously an important issue to look at, and so a dynamic or a plant relevant variable that can really reflect patterns of precipitation or temperature might become more important as we progress. I also want to say that I think that the climate water balance toolkit is really a complex set of variables. So it is taking into account climate, terrain, soil data. So I think that it could be improved, but I do see the merit of it. And from the climate water balance variables, we see that the influence of topography on solar radiation is represented by climate water balance, and that slope position could probably be integrated into this tool set, or like I said, used in tandem with it. I think there's a lot of exciting opportunities for future work. One would be looking at longer term moisture patterns. So I mentioned we took moisture throughout June and October using those microstations. So I think looking at that data could be pretty interesting. I think that the patterns of soil moisture that we see in the field could vary seasonally based on how much moisture there is. So the influences of topographic position might increase or decrease based on the moisture in the field. I also think that measuring moisture at a greater depth might reflect different results. Dyer, who created this tool set, was measuring soil moisture in the field at a greater depth than we were. So he was looking at 30 to 60 centimeters, whereas we were really looking at that surface level soil moisture. I think that looking at different vegetation data could be pretty interesting. So smaller size classes of trees, herbaceous data, and even looking at abundance rather than just looking at presence data. I also think that this framework or these variables might be applicable to studying other organisms, especially those organisms that are relying or studied through moisture gradients. So here are my references for this presentation. I want to take a minute to thank my co-advisors, as well as Dr. Young and Dr. Lotka, who are my co-advisors, Dr. Barton, who served on my committee, as well as UK Appalachian Center and UK Department of Forestry and Natural Resources for funding me and for funding this project. I also want to thank David, Neva, and Erwin, who are Robinson Forest staff, who were always hospitable and making sure we were safe in the field. Lastly, I want to thank everyone who helped me with fieldwork. It would not have been possible without you, specifically Zach, Ben, Brandon, Dan, Alex, Jenna, Kamina, and Thomas. I really appreciate it. And with that, I'll take any questions.